Okay, let's get started. So what I'm going to do today is to essentially give a very brief overview to digital control, which is sort of the last part on control theory. And again, like the last lecture, it will be a sketch of digital control. There's quite a bit more to it that we won't get into. I'll mostly explain why we didn't study it rather than why we are studying it, and do an example, which would be the homework problem from last time. And then we'll move on to probability. I put the text online on Friday, and you've seen it. Most of the material there should be things you've seen before. You probably haven't seen the material on moment generating functions, but that's not something I want to actually cover. The two things I really want to cover in some detail are conditional probability, or three things: conditional probability, random variables, and joint probability. I'll kind of just go over the basics and spend most of the time today talking about conditional probability and to some extent random variables, and then we'll continue with random variables, and I'll kind of probably, depending on how time goes, I might sketch this part on moment generating functions or standard distributions, one of the two, and spend quite a bit of time on joint probability, because that's what you really need for information theory, is a good understanding of joint probability. Okay, so to come back to this, the digital control. So you remember that signals, basically, we have looked at two kinds of signals. These are continuous signals, and those signals which you can think of as having values only at particular points in time. And traditionally, these values in time are coming from a sampling process. So we have an underlying continuous system, and what's happening is that you're sampling it in order to get the digital signal. So this is continuous, this is discrete or digital. Digital actually means that both the values in time and in the quantities are discrete, but we don't, at the moment, we ignore that. And we assume that the digital values are obtained by a sampling process, and what we really need to do in order to capture all the effects of the signal is to make sure the sampling is happening at the Nyquist rate or greater than the Nyquist rate. And then you go to Nyquist rate, where this rate is the twice the support in the frequency. So if you take the Fourier transform of this signal over here, we'll get some hopefully it's band limited, and we can find out the width of the frequency band, and we need to sample twice of that frequency in order to capture all the effects. Otherwise we get aliasing, so we studied that last time. But at any rate, this is how we get the digital signal. That's one way of getting digital signals. And again, if you're studying a chemical process or something, the underlying process is continuous. You know, we have a reactor, we're putting in some chemicals, and you're turning up the heat and so on. And so what you're doing is you're measuring it, let's say, once a second. That's where the samples come from. But you can imagine that the underlying system has some unknown state between measurement times. So if I measure it 1 second, I measure it 2 seconds, between 1 and 2 seconds, it has some temperature. It's not like it doesn't have a temperature. It has some temperature. You just don't know what it is. So that is the meaning of sampling a process. On the other hand, when you consider a computer system or a digital system, the system doesn't change between clock ticks. So you have time signal. You have value in time, like this one. And in fact, it is going to be absolutely steady until this one over here. So in fact, what we can say is that the system is known to not change between these clock ticks. Okay, so each digital value over here represents you can think of it as a continuous signal, which is a stepwise signal. Okay, it's not like we have a continuous signal like this and we're approximating it. In fact, what we have is a signal which is exactly looking like this. Okay, and so when you do digital control, we are actually looking at both things. We can think of the stepwise signal as being the true system, or we can think of the stepwise signal as an approximation to the true system. But then what we do is we treat the input signal, the commands and the process and everything in the system as having the stepwise value. Okay, and that's the basic idea of digital control. Now, in computer systems, since it's inherently digital, you might wonder, why do you want to do continuous time control? And the answer is because of two reasons. One is that when these steps are really, really small, okay, if you look at a gigahertz processor, each step lasts 1 nanosecond, right? It's 1 second, you've done 1 billion of these steps. So when the steps are really, really small, it's basically, you're talking about extremely fine time slices. There's hardly any difference between continuous and digital at that point. Okay, and continuous time control turns out to be much easier, okay, in terms of analysis and so on. So that's one reason to think about it as digital, as a digital system as being continuous. And the second reason is that when you have multiple clock rates, you have this very funny system where some of these signals look like this. Other signals, if I were to draw it using a different color, would be not synchronized with this, and you might end up with one signal that looks like that, the other signal has a different phase altogether and has a different clock tick altogether. And the analysis of this kind of system, to do it properly, actually is basically, well, as far as I know, it hasn't been done. People assume that this is a universal clock tick. Now what you could do then is to find the smallest phase difference between the two, use that as the clock tick, and then make these to be the multiples of that. But it's really messy, okay? And so it's not clear you're going to get a lot of gain, especially when you have this extremely fine-grained clock. So my belief is that you're better off studying a digital system, especially current systems. You're very fast, using continuous control instead of digital control. So that's really sort of why I decided to not present digital control over here. Okay. Any questions about this? Okay, so let's see. If you do digital control, what do? It turns out that you don't do things too differently, at least at first glance, from continuous time control. So the state equations look like this. So xk plus 1 is going to be A, some matrix A. This is the state space representation. Xk plus buk plus f wk, where this is the state, that's the input, that's the disturbance, and then yk plus 1 is going to be cx k plus duk, and they are left out the vectors and so on, but they're the sort of the obvious vectors and matrices, except in the case of SISO, this would be scalar for a SISO system. Okay. Now, what you'll notice is that in the continuous case, we have x dot equals ax. Okay, and here we have xk plus 1 equals axk. So what's going on is that in the continuous case, what we're saying is that the rate of change of the state is some combination, some linear combination of the underlying state elements. Here we're saying that the next value of the state is some linear combination of the state elements, and we can think of this roughly as saying that basically x dot equals x plus x of t plus delta t equals x of t plus x dot t delta t. Okay, so this is the definition of x dot, right? Because xt plus delta t minus delta t minus xt by delta t is x dot. So I can just rewrite xt plus delta t like this, and so we can think of this as xk plus 1 equals some value depending on xk, and so the a over here is not the same as the a over there. Okay, so we're going to have to merge some terms in, because this delta t becomes implicit. Okay, this delta t is implicit, it's 1 typically, and so because we're k plus 1 over here, and so this the point I'm trying to make here is that you can't just take the continuous time value of a and plug it in and get the discrete time of a, because we have a slightly different update equation over here. Okay, but that's really what you're trying to do over here. The other thing is that generally speaking, our x dot is going to be replaced by xk plus 1 minus xk. So the derivative becomes the difference in digital time control, because the derivative, the rate of change, is just going to be a difference. Okay, so we analyze this by taking the Z transform as we normally do, and so the Laplace transform. And so over here, what we do is that we take this one and recall that the Z transform of x k plus 1 is the forward shift operator, and that would correspond to z times x of z. Okay. And this one is going to be a x of z plus b u of z, and again we'll ignore the disturbance as before. And then if we move the terms over, we get basically x of k in the time domain is going to be the inverse z transform, and this looks like the inverse Laplace transform of zi minus a inverse bu of z. So if you remember, we had the si minus a last time, and here we have zi minus a. Okay, so it's again going to be the a matrix that looks, it has the eigenvalues of a, and so we're going to look at to figure out where the to figure out what the value of this is going to be, or where the poles are going to be. We're going to basically take the determinant of this determinant mod zi minus a, and look at the eigenvalue, look at the roots of this equation, which will also be the eigenvalues of a, and that will tell us basically whether the system is stable or not. And the way we do that is that the condition is mod z is less than 1, rather than s is less than 0. So it becomes the equivalent of that in the digital domain is mod z less than 1. Okay. So let me do the homework problem a little bit, and that will hopefully give you some sense of how we go about doing it. So we have the system in the continuous time domain. Here's x dot equals u minus w. So what we're saying is that the rate of change of the buffer is the input rate minus the disturbance, where the disturbance, of course, is our service rate being modeled as a disturbance. And so we write this in discrete time as xk plus 1 is going to be, xk plus 1 minus xk. So that's going to be the x dot is going to be equal to uk minus wk. And if you think about it, what you're saying is that the value of the buffer at the k plus 1 at time instant minus xk is how much the buffer went up or went down, and that's obviously how much came in minus how much went out. So that's basically it. And of course, we are saying that y equals x, so the output of the system, we don't really have an output, it's just a buffer. So we're saying the buffer is the output of the system is the same as the buffer value. So we can just rewrite this as yk plus 1 minus yk. So the change in output is equal to uk minus wk. And if we're going to use proportional mode control. So for proportional mode control, what I said in the question was that we're going to set u equals r, the command r minus y over alpha t. Okay, which what we're saying is that we want to get to the desired value r over alpha t time steps. Okay, where alpha is some number greater than or equal to 1. So the larger the value of alpha, the less, the more gentle the command. Okay, the more gentle the control, I'm sorry. So if you say I'd like to get to the desired value r in 10 time steps, then what u is going to be smaller than if you say I want to get there in 2 time steps. Okay, and of course you don't want to get there in 0 time steps. That would lead to an infinite loop gain. And if you have an infinite loop gain, you have essentially an unstable system, even with the smallest delay. So we want to be careful about that. So we'll choose alpha. Typically, you'll say alpha is 2, 3, something like that. But in this case, we choose alpha. And when we substitute that into this over here, by just substituting it over here for u, we get y k plus 1 minus yk is going to be equal to rk minus yk over alpha t minus wk, and that you can rearrange as alpha t yk plus 1 Okay, so the alpha t yk plus 1 minus, so the yk, there's one yk from there and there's one over here, and so this will become minus alpha t minus 1 yk equals rk minus t wk. Okay, I think, is there alpha t wk? No, just alpha t wk, I think. Anyway, that is just going to go away because we'll set the w to 0 when you're doing our z transform. To take the z transform, we just look at this part and look at the z transform of that and the z transform of that. So this one is going to be okay. So alpha t times, it's going to be z y z minus alpha t minus 1 y of z equals r of z, and then just ignore the disturbance for now, because if you remember, the way we are going to compute the stability is to just ignore the disturbance and just look at the inherent or natural response of the system. And so if we rearrange that, we will get basically y equals r over, I'm just going to alpha t z minus alpha t minus 1. I believe that's what you're going to get. And for this is going to be, and so from this we will find, I'm skipping some steps over here, that this one, the poles are when this is going to be equal to 0, right? That's where the poles are equal to 0. And so we'll get the, sorry, we don't need, okay. So the poles are going to be set when alpha t z minus alpha t minus 1 equal to 0. And this is going to be when z equals alpha t minus 1 by alpha t. Okay, so we're basically saying that the value of z for which the transform value has infinite value, the poles are for that value of z, which is this. So what this means is that we can put the poles wherever we want. We can place the poles by choosing alpha. That's really what's going on over here. T we don't control. T is sort of the system value, right? But we can choose alpha. And this is what we call pole placement. So we're saying that we have this pole, but the pole is parametrized. And why is it parametrized? Because the pole depends on the control action. So this is the basis of control theory. Just to step back a moment, if you step away from the math, what we're doing over here is this. We have a system which is, when it's uncontrolled, it's doing something crazy because we don't really know what it's doing at all. The buffer could be growing too large, too small, whatever. We introduce into it proportional mode control, and now we want to know how is the overall system behaving. And to figure out how the overall system is behaving, what we're going to do is we're going to introduce this tuning knob, which is alpha. Okay, alpha is essentially the inverse of the loop gain. And what we're doing over here is we're finding out those values of alpha for which z is going to be 0. And if it's, so not z equals 0, I should say, for which the system is going to go to infinity. And this is going to be these are the points where when you do the inverse transform, we're going to find the time domain evolution, right? This is where the poles are going to be. So we're kind of skipping all the intermediate steps and just saying, let's focus on the poles, okay? Because wherever we place the poles is where we're going to actually, when we do the partial fraction expansion, etc., we're going to find that's where we're going to get the time decay of the system. So by choosing this value of alpha properly, we can get mod z less than equal to less than 1, and which will turn out to be t is alpha. Okay, we're going to express this in terms of t, I guess. So t is greater than 1 over alpha, or we can say alpha is less than 1 over t, one of the two. If you view this as alpha is given to us, what should be the sort of the time step? We would use this in terms of t. if you view this in terms of the control knob, you'd say alpha is less than 1 over t is going to be the control knob that you're going to choose over here. And when you do this, it's alpha is greater than, actually. And that will tell you the stability point of the system. And in the example in the text, I'd say this is going to be true as long as t is greater than or equal to 1. Now, t is always going to be greater than or equal to 1, right? Because t's are sort of a time step in some sense. When you put in the alpha, alpha is a loop gain parameter, okay? And so you're choosing alpha to be such that we have a stable system. And this is going to be true when alpha is going to be greater than 1 over t. Okay. Now, I know that most of you, when you solved it, and I messed up when I finished up, I said the answer is this. But really, what we're trying to do is how do we choose this tuning knob, which is alpha, and that should be the answer over here. Anyway, the important point here is to realize that in a control system, we're always going to end up, we always would like to end up with this value over here, the tuning knob, and we want to set the tuning knob so the system is stable. And essentially all we're saying over here is that don't try to be too greedy and make the system converge faster than the inherent time step t. As long as you're going to work for more than that, it's going to be okay. And because it's proportional mode control, it's inherently stable. You don't have problems that you would have typically with differential mode, for example. Are there any questions about this? Yeah?
I think t is greater or equal than.
Greater than or equal to. Well, the thing is, for stability, we want the pole to be less than we want the pole to be inside the unit circle.
Yeah, but if you set it to 1 over alpha, it's 0. Z is 0.
Okay, wait a minute. It's t is equal to 1 over alpha. Oh, I see. Okay, so say that again. Right.
Z is 0.
So t is 1 over alpha. So what you're saying then is that over here, that's where the pole lies, right at the center, z equals 0.
Yeah.
And so that just, I mean, that's okay. It's inside the unit circle.
Yeah, but I'm saying that the requirement for this to be stable is t is greater than or equal.
Oh, I see. So it can be greater than or equal to because z is 0 is okay. I'm sorry.
So like you have the final answer, right?
Yeah, I'm saying alpha, yeah.
And it can be greater or equal.
Equal to, okay, just give me a second over here. So, yeah, I think it should be, okay, you're saying alpha could be greater than equal to 1 over t. If alpha is equal to 1 over t, then we're going to get z equals 0. Okay, that's actually going to be fine. So yeah, it should be equal to, okay, I got it, yeah. So this should be equal to 1 over alpha, sorry, right, yeah.
Because in example, alpha is greater than 1 and not equal to 1.
Right. No, the thing is that the direction it's going is towards the center, not towards the border. Okay, so we don't want it to be on the unit circle. And I think what Jacob is saying is, don't worry, it's on the unit circle. It's going to be at the 0 point, not at the center circle, at the edge of the circle. So I'm kind of giving you a very, I'd say, rough sketch of how things are done. But the 2 points I want to take away, one is that we're going to start with this and do everything with the Z transform rather than the Laplace transform. And the second is that we are going to be focusing in all the control. We always try to come up with a knob, we call it KP, which is our tuning knobs, and we place it so that we're going to have a stable system, in this case, we've got the KP, the proportionality constant to be alpha, and we're going to choose the alpha such that the poles of the system are going to be inside the unit circle, and then we have a stable system. Okay, so that's the general direction which we proceed. There are many complications with digital control having to do with dealing with aliasing and dealing with the different kinds of sampling frequencies and so on and so forth. And I'm really not going to get into that at all. This is really a very high-level sketch. Okay. Okay. Any questions about this? Yes. So I think that in the example, I guess, yeah, anyway. So the example in the book, I was saying basically that if you're going to just choose the loop gain to be Oh God, what am I doing here? Okay, sorry. So t is a parameter as well. I'm really not. Okay, so we're coming. I'm confusing t and 1. Okay, so t is a parameter as well. Oops. Why did I think t is the time constant? Okay. All right. Okay, how about that? That's actually better because I just realized that I was assuming. So in digital control, we can assume that the steps are at t, 2t, 3t, etc., or you can assume they're at 1, 2, 3. Oops. And for some reason, probably having to do with my advancing age, I confused this system and this system. So we're using this system where you're always doing k plus 1, not k plus t. So t actually is the time at which you want the system to be stable. So this is, okay, this is correct. If you're confused, I don't know. Okay. Okay. Do you get what's going on? Okay. If you have a system where capital T is used to represent the time step, then T is inherent to the system because this is the first time step, second time step, and so on. And so that's why I was saying that T is not under your control, only alpha is under your control. Actually, now that I read this more carefully, I said, suppose the system wants to get to the set point after capital T time steps. So we're having this system over here. So T is actually also in your control. So you actually have two control parameters, alpha and T. Okay, and so we just want this thing to be true. Alpha T is greater than or equal to 1. Okay. I'm sorry, it's not greater than or equal to 1. T greater than or equal to 1 over alpha.
Yeah, how do you come to this from?
The thing is that the z is going to be the value of z for which this function is infinite. The poles are the values where this function is going to be. So we know the poles are going to be where this expression on the bottom is equal to 0. Okay, maybe I shouldn't say z equal to this. I should say. Sorry. So let me draw this better over here. So this is the complex plane, the complex z plane. Okay. And we're looking at y equals r over alpha t z minus alpha t minus 1 as being the function. Okay, we want to know for what value of z is this value infinite. This value of so that we call the pole. Okay, so the pole could be some value of z for which value is infinite. This could be some arbitrary values of z for which the poles exist. So this we set to 0. Okay, if we set this expression to 0, that's what we get. So we're saying, okay, for this value of z, okay, is where the poles are. Okay, and so we want the poles to be inside the unit circle. So we're saying this thing should be less than 1. Okay, in magnitude. So we get, and then if you solve that, once this one should be less than or equal to 1.
But that will be always less than equal to 1. Because alpha is greater than 1 in the question and t is positive.
That's right. So if alpha is greater than 1, t is positive, then this expression is always going to be true. Right? So that's what, so you will actually get that. Okay, but if you said alpha to be less than 1, also it will work. But in the as stated, if alpha is greater than 1, then we're going to say, yeah, sure, the poles are always going to be inside the unit circle. Okay.
I'm doubtful actually. Mod z less than 1 is probably going to give some other solution.
Yeah, so it looks confusing, and actually I spent quite a bit of time thinking about it. What's happening is that mod z less than 1 is kind of funny. When we actually going to have negative values of z, and if it's too small, it'll go outside the unit circle. So just think about it for a moment. Okay. It is confusing. If you take z less than 1 and mod z less than 1, these are actually different things. Okay, so yeah, that one I'm sure of. Yes?
I think it should be 1 over 2, sorry. 1 over 2 alpha.
1 over 2 alpha. Okay, let's just do this properly because I was, okay. So this is the equation, right? Why should be 2 alpha?
Because if you consider the minus 1.
Okay, so we are saying, okay, this is mod z, so we should say either alpha t minus 1 over alpha t is less than 1 or, okay, and actually it's not an or, is it, and 1 minus alpha t over alpha t is greater than 1, okay? Minus, yeah, it's also less than, sorry, yeah, less than 1. So this,
It should be greater than 1.
okay, let's see, we want, so negative of this is, I want this to be less than 1. This is less than 1, and then negative, so, okay, let's just do this. This is correct. I just want negative of this should be less than 1, right? It's not, yeah. Don't confuse me, Raymond, okay? Otherwise, I'll ask you to come to the board and do it, okay? As my colleague was saying, the minute you hold the chalk and stand on the board, all your math just disappears. You can't do anything straight. Okay, so let's do this properly. So this one means that alpha t minus 1 is less than alpha t, okay? And this is going to be true for, well, okay, so this is going to be always true basically for alpha t positive. Greater than 1, sorry, alpha t greater than 1 is, this is all, okay, let me, okay, so, yeah, this is 0 less than 1, so this is always true. So this is always true. So this one is going to be 1 minus alpha t is less than alpha t, okay, so 1 less than 2 alpha t, okay, so 1 over 2 is less than alpha t, so alpha t greater than 1 over 2, or t greater than 1 over 2 alpha, okay, so you were right, okay, so that's the way that works. So that's the answer. And I think some people said alpha is positive, so this is value between 0 and 1, and the time step value is always going to be greater than 1, because so t is going to be at least 1, because we're in this domain over here, so t greater than equal to 1 is also going to be true, which is fine. That's also acceptable. Okay. Any questions about this? I think I really did it properly this time. I was skipping too many steps. It's always a mistake skipping steps. So there's a lesson to this, which is that every step is important to get the right answer. And if you try and skip steps, even if I try and skip steps, you get the wrong. I got the wrong answer. So anyway, sorry for the confusion. Okay. It doesn't happen too often, but as I get older, it happens more often than I'd like. All right, I'm going to now finally move out of this control theory and into probability. Most of you have had some introduction to probability by now, so I'll just double check. So how many of you have done some course in probability in the last, let's say, 3 or 4 years? So pretty much everybody's done that. So I'm going to go through this pretty fast, and I'm just going to try and hit on the high points. The text is pretty self-explanatory, and it's also the first chapter in the book, so it starts out slowly. And what I'm going to do today is to focus on just some terms and some concepts which you're going to find useful later on when we do information theory. So a couple of things. So one is this notion of outcomes, events, and sample spaces. Okay, so when we talk about probability, we often don't talk about where is this probability coming from. Okay, and in any reasonable discussion of probability, you need to understand that there's an underlying sample space, and in this sample space, we have outcomes, and these outcomes form sets called events. So maybe the easiest thing is I'm actually going to go through the homework problem, because that gives a reasonable place for us to hang our discussion on from a concrete example. So what we want to do over here is you have a buffer which has got 10 elements, and we classified them